Good evening, everyone. My name is Sridhar, and I am from Computer Science and Engineering Department. Today, my AAT Tech Talk of the subject Computer Science and Architecture is Virtual Memory Issues of Implementation in Computers System and Architecture. Virtual Memory Overview. Virtual memory is a memory management technique that allows the use of disk space as an extension of RAM. Here, it enables system to run larger application than physical memory alone would permit. Implementing virtual memory involves complex hardware and software coordinations to manage data transfer efficiently. Here, the virtual memory is a management technique which allows to use a disk as extension of RAM, which is random access memory, and it also enables to run larger applications in the physical memory and would permit. And implementing virtual memory involves complex hardware and software coordinations to manage data transfer more efficiently. Purpose of virtual memory. Virtual memory provides process isolation and protection by isolating each process address space. It allows multiple applications to run simultaneously without exhausting physical RAM. This technique improves system responsiveness and overall performance by optimizing resource utilization. Here, the virtual memory provides a process isolation, which means gives a protection to the address of the data and also gives multiple application to run simultaneously along with the physical random access memory. And also this is useful in the techniques to improve the responsiveness and overall performance by optimizing the and resource utilization. Basic virtual memory architecture. Virtual memory uses address translation mechanism like tables to map virtual addresses to physical addresses. It employs a combination of main memory and disk storage to hold data per active process. The architecture typically involves components such as memory management unit (MMU) and page frames. Here we can see, I can explain you with this diagram. Here we have a computer memory, which is further divided into virtual address, where it goes into translation, where virtual memory uses address to translation the mechanism like pages and tables and to map virtual addresses to the physical address. So from the physical address go to the virtual memory, to the cache memory, and then to the main memory and perform a task. So here we can see it employs a combination of main memory and a disk storage to hold the data and retrieve process. The architecture typically involves components such as MMU, which is also known as Memory Management Unit. Now let us discuss about the issues of implementation in the virtual memory. Here we can see the issue 1, fragmentation. External fragmentation occurs when free memory is divided into small non-contiguous blocks. Here, the external memory is divided into small and non-contiguous blocks, and internal fragmentation happens when allocated memory blocks hold unused space with them. Fragmentation can reduce the efficiency of virtual memory utilization and increase the overhead. Here, the huge memory is divided into small pieces and also uses for the non-cognitious blocks. Here, the internal fragmentation happened only allocated memory to hold the space with them. Issue 2, the page replacement policies. Here, when physical memory is full, the system must decide which page to swap out, leading to page replacement. Common policies include FIFO, LRU, and optimal algorithms, each with different trade-off. Inefficient page replacement can cause increased page fault and degrade system performance. Here we can see there is a common policies include FIFO, which is a first in first out, and the LRU and optimal algorithms, which use trade-offs. Here the physical memory is full, then the system must decide to whether the pages to be swap out or to the leading page replacement. Issue 3, page fault handling. A page fault occurs when a program accesses a page not currently in physical memory. Handling page fault involves disk IO, which is significantly slower than the memory access. Excessive page faults can lead to crashing, severely impacting overall system efficiency. Here we can see that there is an operating system where the page is on backing store, and then there is also a page table and a load M. Here we have a reference and the restart instruction and a page table. Reset page table where you can get a free frame. Bring in missing. Here we having a physical memory. Issue 4, TLB management. Here the TLB means the translation look aside buffer. The translation look aside buffer TLB catches the recent address translation to speed up access. TLB misses require accessing the page table, adding latency to memory operations. Managing TLB entries efficiently is critical to maintaining high system performance. Here we can see that a virtual address TLB access, where the TLB hit to the physical address where you can see a catch hit, and you can clearly see from this diagram. Issue 5, synchronization and consistency. Maintaining consistency between page tables and physical memory is crucial in multiprocessor system. Synchronization mechanisms are needed to prevent data corruption during concurrent access. These complexities add overhead and can complicate virtual memory implementation. Here, the maintaining consistency between the tables are most important in physical memory is crucially for multiprocessor systems. Issue 6, overhead of memory management. Here, virtual memory management involves additional hardware such as MMUs and page tables, increasing system complexity. The overhead includes time spent on address translation, page fault handling, and page replacement. Excessive overhead can negate the performance benefits of virtual memory if not optimized properly. Issue 7, security concerns. Virtual memory provides isolation but can be exploited through side channel attacks. Protecting page tables and TLB entries from unauthorized access is essential. Here, implementing security measures add further complexity to the architecture. Here, the virtual memory provides an isolation but cannot be exploited, can be exploited through side channel attacks. Here, we are having the protective pages, protecting the page tables and TLB entries from unauthorized access is very much essential. Implementing security measures add further complexity to the architecture. Issue 8, hardware constraint. The design of hardware component like the MMU impact the efficiency of virtual memory. Limitations in hardware speed or capacity can bottleneck virtual memory performance. Upgrading hardware to support advanced virtual memory features involve significant cost and engineering effort. Here we can see with an example. Here the virtual address page number is offset, where we are having frame by frame, where this is known as paging mechanism. And we also have a page frame number and offset to the main memory. Issue 9, scalability challenges. As system grows with more cores and larger memory, virtual memory management becomes more complex. Ensuring ensuring consistent and efficient address translation across multiple processors is challenging. Scalability issue requires sophisticated algorithms and architecture to maintain performance. Here we can see the system is growing with more cores with a larger memory. Virtual memory management becomes more complex and which become very difficult to manage the virtual memory. And scalability issues require sophisticated algorithms and architecture to maintain good performance. Strategies to mitigate implementation issues. Using efficient page replacement algorithms reduce page faults and fragmentation. Implementing hardware support like large TLBs and multi-level page tables enhances performance. Regular system tuning and memory management optimization are vital for effective virtual memory use. Here, the regular tuning, serial system tuning and memory management optimization are plays a vital role, plays an effective role for the virtual memory use. Future trends and improvements. Emerging architecture focuses on hardware, software, and co-design to improve the virtual memory handling. Techniques like adaptive page replacement and smarter TLB management aim to reduce overhead. Advances in hardware such as non-volatile memory may reshape virtual memory implementation. Here we can see the future of computer architecture is an emerging trends. We can improve with using the hardware and software co-design to improve the virtual memory handling. Virtual memory is essential for modern computing but present Several implementation challenges, overcoming issues like fragmentation, page faults, and hardware constraint requires careful architecture design. Ongoing research and technological advancement continue to optimization to virtual memory systems for future needs. Here, it is more important for the virtual memory to is essential for the modern computing, and also so we are overcoming these all the issues like fragmentation, page faults, and hardware constraints requires careful design architecture. And this is a summary and conclusion of this topic: virtual memory issues of implementation. Here there are the references where I got this all these things from. I mean the PPT from the books like Silverance, operating system concepts, and here we can see those things. And this is all about virtual memory, issues of implementation of virtual memory in computer structure and architecture. And thank you.